homework on chapter 14. Everybody missed a question, so I'm going to do it with you guys. The very first one. Yeah, we're going to be doing 15, but I want to do this question with you guys first. Okay, so I'm not going to copy the whole thing down. It says, imagine a square is a piece of paper lying on a table. The side facing you is side A. The side hidden from view is side B. Every motion of the square either interchanges the two sides or leaves the sides as they are. In other words, you either have epsilon or alpha here. Verify, they define, call G of Ri the G of Ri, that's the rotation or the flip, is going to be equal to epsilon if Ri is a rotation, and it's equal to alpha if Ri is a flip. Those parts, that part you guys got right, but then when you broke it up into your cases, you started miscalculating it. Yeah. So the hypothesis, we're going to go to straight down to the cases, because that's up to the cases everybody was correct on what they did. The first case is, of course, that you're going to have Ri and Rj. You guys call them A and B, so let's call them A and B, so it matches your work. You have A and B are in the rotations, and I think you call the rotations 90, 180, 270, and 360, so I can put those down here. I'm going to call R360 R0. If A and B are in the rotations, this part you got right. G of A is going to be equal to epsilon, and G of B is equal to epsilon, and two rotations is also in your set of rotations. So G of A composed of B is equal to epsilon, and then you can show that G of A composed of B is equal to epsilon is equal to epsilon epsilon, which is G of A, G of B. So far, so good. Now your second case, and this is where things got a little strange. You put A and B are still in the set of rotations. You've done that case. Now you're going to have A is in the set of rotations, and B is in the set of flips. 1, 2, 3, 4. There's 4 of them. And then, what does that tell you G of A is equal to? G of A is epsilon, and G of B is alpha. And A composed of B, if you do a flip and then rotate it, it is change the sides, so that is going to have, we'll just do G of A composed of B immediately. That interchanges the sides, so that has to leave you with alpha, because the flip gave you an interchange on the sides. So that goes to alpha. Thus, G of A composed of B is equal to alpha, But if you go and look at the table, which you guys all got right, it's epsilon alpha. Epsilon went together. Epsilon alpha gave you alpha, and then alpha gave you epsilon, back to the original. So if you go up here to the table, alpha can be written as epsilon alpha, which is what we need because G of A is epsilon, and then G of B is alpha. And then what happens on the next case? What would be that case? A and B are switched. A is in the flips. And B is in the rotations. Then G of A is equal to alpha, and G of B is equal to epsilon, and G of A composed of B. Now you're doing the rotation first, and then the flip second, but still it stays as a flip. It leaves the opposite page up, opposite side of the page up, so you get an alpha for that. And G of A composed of B equals alpha is equal to alpha epsilon is equal to G of A, G of B. And then the last case is the both in the flips case. You didn't ever interchange the two cases. You either always said they were both in rotations or they were both in flips. And then you misapplied the G part on it. So either you copied and pasted and everybody copied and pasted wrong, or there's a misunderstanding. So I'm going with, you guys know better than to all copy and paste wrong. I'm going with there was a misunderstanding. What is G of A then in this case? It's a flip, so it's alpha. And G of B, I forgot the end. Now, if I flip it and then flip it again, we're back to the same face up. So this is going to be epsilon. But epsilon is also alpha composed of alpha, which is G of A, G of B. And then your conclusion was correct. It's just the work on the cases wasn't quite right. So I wanted you guys to have that corrected. And I didn't want to write it down. I forget, I think 9 times. Some people haven't finished it yet, so now I have the answers. Okay, so there is that one from the homework from last time. Oh, I guess I am working on one of these with you guys. Consider this group G, which is Z and plus. I forgot I'd assigned this as classwork, so yeah, this is class extra credit work. Get into groups here again. Groups of 3 or 4. And what you're doing is determine the elements of the quotient group, G mod H, and find the order of each element. In other words, what is G mod H equal to in set notation? And then give me the order of each of the elements in G mod H. H is the 0 cyclic group of 0. What are the elements in that right there? Yeah, it's just 0. So I couldn't give you an easier problem for the first thing in the morning. List all the elements in G mod H and then give the order of each of them. H is 0. Those are the elements in H, but what is G mod H?
Oh, yes. Sorry, I thought you were talking about the H function. I see what you're saying.
Adding 1, adding 2, adding 3. Is that an addition? But if it's 0, is it gonna look around like the other one? Or does it go under?
Well, ask yourself this question. What is a cyclic group of generated by 2? List all the elements in that set.
Well, that goes on for infinity.
Does it ever loop around?
No.
No. Okay. Can you just sleep here at night or something?
So that's fine.
Right in the morning. And I want to sit out here every morning at 7:30.
Do I need to say 0 plus or do I say H plus?
That's still really good though.
Say what? H plus, you don't have to say 0 plus, that's correct.
So just I agree with marvelous.
Just, yeah, go talk to that.
So it would just be like H plus 1. I'll leave it.
Doesn't really need any more
Okay, so. Well, I didn't do the set, I didn't do it for last week.
No.
Thank you. Yeah.
Well, as long as you can identify what they all are. What order?
It says determine that elements of a given group, find the order of each element.
Yeah, the order of H is 1.
Right.
But what is the order of all the rest of them? The order is the number of elements. Why?
Because it's cost gravity.
Yes. Now explain that to Luba.
The order of each element is infinity?
Dalton wants to tell you why.
G goes up forever, so the order of infinity because that's how many elements.
Right, but it's asking for each element, not the set.
together to get back to
Exactly.
Have you listed those elements? What are those elements?
When you have G slash H, you do that like A have H, B have H, C have H.
So let's start looking at those elements. What are A, B, and C? Let's give some values. H plus 0 is just
I'm just verbalizing it. Sorry,
H.
sorry, that sounded like.
But what would H plus 1 be?
All this addition from now, I start off multiplication.
It's addition, it's addition. I specified addition.
Sorry.
It's the same operation.
Can I just say this?
I still don't understand. But I get why this said G is infinity.
Okay, so what are elements in H? You have H plus 1 is 1. What are all the elements in that?
Oh, H plus 1. Oh, yeah, 0.
But one is one, but two is two, but three is three.
Yeah, adding 1 to itself. You have 1 in there. In fact, or minus 1. You're adding 1 or minus 1 to itself.
Oh, so everything on it becomes cyclic.
Except it's not a finite group. Yeah.
But it becomes that same defense.
H plus 0.
What would H plus 2 be?
Internal to the brackets too.
Mm-hmm. And what group is that? What are the orders of all of those? Infinite. Mm-hmm.
Oh, we just have randomization.
Or you can write it this way.
Yeah, that's better.
Yeah, this is
It's
just like.
just like, oh, yeah.
Should I read this?
And then what's the order of each of them?
Are they all except for the first one?
Except for the first one. Order of H is 1. And then the order of H plus I not equal to 0, is infinite. Mm-hmm. The whole point of that was remember what cosets were, quotient groups are. Do we remember that from before? G mod H? Those are quotient groups. Mm-hmm. Okay. Do we have that down on our papers? Okay. I suppose I could make this. You didn't write it? Evidently not where she could see it. Oh, okay.
Oh, you made that part.
She wants to be able to study it later, Kalai. It's always a good thing.
Our test is a week from today.
Yes, a review is on Thursday. And no, Dustin, I have not written the test yet. He's not here, but he'll be watching it and he'll wonder. Okay, so let's look at examples. These are similar to your homework, so we're going to work through some of these. Let G be an abelian group and let H consist of all the elements of G which have finite order. Show that H is a subgroup of G and conclude that H is a normal subgroup of G. So that's the first part that we're going to do. By the way, what's the hypothesis statement?
That G
Mm-hmm.
H consists of
This is when you wish you had cut and paste. Yeah, but this is a PDF document. I can't copy and paste it. Okay, we have to show that something is a subgroup. How do we show a subgroup?
Close.
That would be a
No, you're right. Close.
Group.
Close with respect to operational.
close with and inverses. Yes. So let's do close with respect to the operations. So let A and B be elements of H. The definition for being in H is that H has finite order, the elements in H have finite order. So that tells me there exists an M and an N in the natural numbers such that A to the N equals E and B to the M equals E. Now I want to put both the elements together, the product of them, because I want to show that the product is in H. So what power do you think I should use for the product here to get down to the identity? I need an N on the A, I need an M on the B.
M plus N?
How about times? I need them both, right? Now, this, since H is a billion, well, since G is a billion, H is a billion. So that means I can interchange it and I can write this as A to the N M, B to the N M. But that is equal to A to the N to the M. And now I'm going to write this as B to the M to the N. That's by our laws of exponents. But what is A to the N? E. So we have E to the M. And what is B to the M? E. So E to the N. What is E to the M? So that gives us E. Thus, AB has finite order and is therefore in H. So H is closed under the operation. Now, I need to show that it contains its inverses. I know if A is in H, A is in G. And so I know that A inverse is in G. Let's look at A inverse. I know A to the N was equal to E, so I'm going to look at, well, let me get it because I said for each. Also, since A is in H, there exists an N in the integer in the natural numbers, such that A to the N is equal to E. Now I'm going to look at A inverse to the N. By the laws of exponents, that is equal to A to the N inverse. We can interchange those, we proved that. But what is A to the N? E. And what is E inverse? E. Thus, A inverse is in H because A inverse has finite order. Therefore, H contains its inverses. Closed with respect to inverses, however you want to write it. So H is a subgroup of G. Since G is a billion, H is a billion. Now, what do we know about a billion groups and normal groups? One of our theorems from last time. Oh, and that subgroup, a normal group.
Oh.
Yep. From last class period. H is normal. I'm going to put a normal subgroup. Okay, so H is a normal subgroup of G. Now, we have to look at number 2 right here. show that in G mod H, no element except the neutral element has finite order. Now think about the last example we just did. Z under addition, was that an abelian group? And the elements of our subgroup H, finite order or not? Did H have finite order? The elements in H have finite order. Yeah. It was just a 0. 0 is the only element in our set. If we made H be 0, that is just a set 0. When you add 0 to itself, you get 0. Subtract 0 from itself, you get 0. So this had finite order. Therefore, the example that we did is sort of a motivation for this example right here. The only element that we had in G mod H that had finite order was H itself. H was the only one that had finite order in G mod H. Everything else had infinite order. And that's what they're asking us to show. Let me put another paper here. Scroll this up a little bit. This is going to be our number 1. This is going to be 2. So we have to show that these have finite order. How would we show that they have finite order? What does it mean? We're not.
They can find at least positive integer.
Yes. Let Hx be in G mod H for some x in G. And then consider the powers of Hx. What is that going to be equal to? How many times is that multiplied? N times. But from last time, I know that that's going to be equal to hx to the n. You don't multiply the h's, it's just the x's that end up getting multiplied. So I have to look at hx to the n. How do I determine the order of n, the value for n? If think about this way. If there exists an n so that this is equal to e, then x is in h by definition of h, correct? H is everything with finite order. So if there exists an n such that x to the n equals e, then x is in h. And so by the theorem that theorem 5, which we proved last time, hx to the n equals h if and only if x lives in h, implies that hx has finite order if and only if x is in h, but then that means that if x is in h, you just have h. Thus, h equals hx. Well, I'm just going to say it this way, I'll confuse you. Thus, h is the only element in G mod H with finite order. Because if x is in h, then hx is just equal to h. If X is not an H, then X doesn't have finite order, which means HX does not have finite order. That's what that means. So that's just a use of Theorem 5, Part 2. You're actually going to use that Theorem 5 on your homework in a couple of different problems. So that argument that we just went through right there, you're going to use on your homework. Not necessarily in the same way dealing with finite order, although one of your questions deals with finite order. But you'll be using that theorem. It's a very useful theorem. And then the last part of this one said, note that this means that we have factored out all the elements of finite order and produced a quotient group G mod H whose elements all have infinite order except for the neutral element, which necessarily has finite order. So when we made our quotient group, what we did is we have all the elements in G that have finite order, and they're in H. All the other elements in our quotient group have infinite order. So we factored out everything with finite order, and everything else has infinite order. That is what our quotient group does. You are going to have to give this verbal description on your homework problems. That verbal description is part of, I think, 2 or 3 of your homework problems. So don't forget it. It's going to ask you for that verbal description. Any questions on that? Okay. Now, a couple of definitions. Well, a definition. Let G be an arbitrary group. By a commutator of G, we mean an element of the form AB, A inverse, B inverse, where A and B are in G. This is a definition of a commutator. This is not the elements A and B. We're saying an element in G that has that form, AB, A inverse, B inverse. Now, if you were looking at BA inverse, we know that's equal to A inverse, B inverse. So if you're thinking about this, AB, this would be AB times BA inverse. That's what your commutator actually is looking like. That's what we're going to be looking at. The following in S3. S3, remember, is on page 71. So go ahead and turn in your books to page 71. I think 72 actually has a table. That's what we need. Yeah. So let's look at, I just picked beta and alpha. We could have picked any number of things, but beta, alpha, then beta inverse, alpha inverse. So how do you evaluate that? We have to find out what beta inverse is and what alpha inverse is and plug them in. What is beta inverse? How do you figure out beta inverse? Look for epsilon on your beta row, and what gives you that epsilon? Delta. So beta is on some row, and some column up here gives you delta, and that gives you epsilon. Delta is equal to beta inverse. So I plug in delta here. So tell me, what is alpha inverse? Alpha. So we plug in alpha right there. And now you have to evaluate delta alpha. So delta is on the row, alpha is on the column. What is delta alpha? That's going to be gamma. So we plug in gamma. Now we have to evaluate alpha gamma. Alpha. So that gives us beta. And then we do beta, beta, delta. So there is the answer to our commutator. Okay, the commutator is this right here. That's the commutator. The answer to the commutator is this right here. Okay, do you guys see the difference there? The commutator is of that particular form, and then you have to evaluate it to get to the answer of that commutator. Okay, you have to understand commutators for us to be able to do our example right here. Let G be a group and H be a subgroup of G. If H contains all the commutators of G, then G mod H is a billion. That's what we're trying to prove. What's the hypothesis for this statement? G be a group and H be a subgroup of G. Yeah. Let H contain all commutators of G. Now, if you try and say H contains only the commutators of G and prove that H is a subgroup of G, you'll be stuck. You need more information than that to prove that it's a subgroup of G. So you have to, that's why we started with H is a subgroup of G. Assume that H contains all of its commutators. Show that G mod H is a billion. Okay? You can't actually show that H is a subgroup without more information. So, how do I show that G mod H is a billion? How do you show something is a billion? Commutative. Any two elements show that they commute. What are elements in G mod H?
No idea.
Gut reaction. This should be H, A, and G.
But don't we need two elements?
Yeah, so we're going to get two elements. So let H, A, H, B be in G mod H. Well, we assume that A is in G, so we're not going to re-say that. So now we need to consider the product of them, right? What is HA, HB? We learned that in one of our theorems last time. Let's see what that's going to be equal to. It was on the quiz, if you recall. Yeah, it's HAB. It's actually from chapter 14, not chapter 15. But yeah, it's HAB. Now, we have these commutators. They have to come into play here somehow. How do I use my commutators here? Yeah, well, I want to look at this HAB.
So now we can use
HAB equals to HBA. Back to theorem 5. What does theorem 5 tell you? Theorem 5, part A. If and only if. So I have HAB is equal to HBA. If and only if, what should we put? AB from the first, and then BA inverse. Okay, I'm going to have to put this on the next line. Has to be in H, right? That's exactly right. Almost. AB, BA inverse is equal to AB, A inverse, B inverse. Element of H means what? The commutators. But that is how we defined H. So if this is an H, this is true by hypothesis, then you go back and that says, thus HAB is equal to HBA, and then take it one step further. You have HA, HB is equal to HAB equals to HBA is equal to HB, HA, and so G mod H is commutative. I'm going to say a billion.
Wait, for a billion I have to prove.
Commutative.
Just
Mm-hmm. Right there and right there. Yeah, we already know it's a group. We assumed it was a subgroup.
Yeah.
So do we used this step here earlier with the commutators just as a verification to know that HAB is equal to HBA?
Yeah. We have to have that commutator in H to know that. Mm-hmm. Are there any other questions on that? Okay, that process, Theorem 5, is going to be your friend on your homework. It's not always going to be obvious when you're starting it, but Theorem 5 is your friend on your homework. So make sure that you're using it where applicable. There'll be a couple of problems that you don't use it, but on the ones that look really strange, Theorem 5 is going to be what helps you with it. We are done with chapter 15 for today. Let me stop the recording. No, it's through chapter 14. 10 through 14. Review is on Thursday. This homework is also due on Thursday. And test is on a week from today. No, you guys won't ever remember it after studying for the test. Kalai was trying to postpone the homework.